Alright, before we get to the topic of a hand, which is simple harmonic motion, I want to talk about one major thing that I noticed during the lab on Monday. And that is that we have to be very careful about how we analyze data. Now, the reason why I say this is that a lot of people I could see were looking at the numbers that they were getting and taking them for face value, saying that if there's a difference, even a small difference, it meant that there had to be a big difference caused by that variable. For example, I saw some groups when they set up their pendulum, maybe they had a small mass here, and then they did the same length, and then they did a really big mass, a mass that maybe was 4 times or more massive. Now, when they got their data, then maybe they found a number of, let's say, 1.98 seconds and 1.92 seconds. Well, there is a difference of those two numbers, but it's only 0.06 seconds over really a value of almost 2 seconds. Now, that's a very, very small difference overall. And so that difference between these two numbers could be really negligible. They could be really telling us the same thing. There could be really the only reason causing the difference maybe just because of the way we measure the data. And so we have to be very careful about how we look at numbers. Does that number actually mean something? And oftentimes, if we're not sure, we do an experiment over and over and over and over again until we get values that are going to actually show us something. Now, two people can look at the same exact numbers and see two completely different things. I would look at these numbers and I would say, hey, there's really no difference. But a lot of you are looking at the numbers and saying, yes, there was a difference. And that could be very misleading, especially in the case of trying to figure out what causes a difference in the period of a pendulum. So, on that, kind of move forward, thinking about that in the back of your mind, let's talk about simple harmonic motion. SHM stands for simple harmonic motion. Now, simple harmonic motion is just a vibration about an equilibrium position in which a restoring force is proportional to the displacement from equilibrium. Now, what this means is that we have something moving back and forth about an equilibrium. In the case of this pendulum here, equilibrium is the middle point. And the restoring force here is, of course, gravity. And gravity is the main thing we're kind of looking for. Now, give me 1 second here. Switch my pen color to, let's go red. Now, I'll rewrite that. Gravity is our restoring force. And it's proportional to the displacement from equilibrium. The farther we get, there's actually a greater force kind of pulling it down. So a pendulum moving back and forth across the middle is an example of simple harmonic motion. And so it's moving back and forth, being pulled to the same point by gravity. Now, in different types of simple harmonic motion, there are certain things we can measure. Amplitude is the displacement. So we talk about how far away is the pendulum from the point. The period, the time it takes to complete one cycle, and the symbol for period is a capital T. That's the time it would take to go from here to there and then back, because that's really one complete cycle. The frequency is how often. How often does it complete a cycle? And we use the lowercase f for that. Now, of course, time it takes to complete one cycle, this is going to be measured in seconds. How often is actually going to be 1 over seconds. And the 1 is 1 cycle per second. That's frequency is measuring that. Now, cycle over second, one of these is equal to 1 hertz, or capital H, lowercase z. So frequency is measured in hertz. Now, the nice equation we need to know for today, the first one, is that period is equal to 1 over frequency, or frequency is equal to 1 over period. They are the inverse of each other. So it's a very simple equation to look at. Period, time it takes to go for one cycle, figure out how many of those we get over time, just take 1 over the period. Now, period of pendulum, what affects it? Well, we have a couple variables it could be. Well, it could be mass. It could be the length of the string. It could be gravity. It could be the type of string. Now, if we think about this in an ideal situation, which means no friction, and no air resistance. So no resistive forces really. Mass plays no role. It's only the length of the string and gravity. And the period of the pendulum can be equal to 2 pi square root the length of the pendulum divided by the acceleration due to gravity. So the period of the pendulum is equal to 2 pi square root length over acceleration of gravity, the 9.81 meters per second squared. Now, of course, this could change. If we go to the moon, a pendulum is going to swing back and forth at a different rate than if we are here on Earth. So that plays a role. And the length plays a big role. Now, look at this relationship for a second. If you actually graphed your data, or if you compared length to period, you would not have seen this very easily. If you graphed length times period squared, you should have gotten a linear relationship. So that's sometimes where graphing data will help lead us to that. If we just graphed length versus period, we probably would have got a nice curved line, and then that sends us in all sorts of different directions trying to figure out what it is. But period of the pendulum is set by the length and acceleration of gravity. Now, one thing hopefully you noticed during the lab was that the pendulum started moving, well, it started changing directions, and that was due to the fact that the Earth is spinning underneath. There's no forces acting on it causing it to change direction. What is causing it to change direction is our viewpoint. And we were spinning. It wasn't. And so it actually seemed to move when actually we were. Now, if I graph the motion of a pendulum, let's say the displacement over time, we would actually get a nice curved graph. One of those nice little sinusoidal graphs we know so much. Now, if we were to graph the velocity versus time of the pendulum, we would see something that kind of looks like this. Because we would be slowing down, stopping at one point, then speeding up, getting really, really fast in the negative direction at one point, and then slowing down, stopping. You know, we're kind of in a motion kind of like this, where our velocity is positive in one direction, negative in the other, and we're going faster and slower and faster and slower. Acceleration-wise, it would just... Another example of simple harmonic motion is a mass that's attached to the spring. First off, I'm going to have to state here, no friction. And so let's say I have this box here, I have a wall, and I have a nice little spring in between the two. Now, if I compress this spring, it'll, of course, remember, store potential energy in the spring, and then if I release it, the mass is going to bounce back and forth, 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 back and forth. And so that'll be another case of simple harmonic motion, because we do have an equilibrium point, and the restoring force is the force caused by the spring. Remembering that the force caused by a spring is equal to negative kx, or k is the spring constant. And if I rearrange this equation, I can calculate my spring constant by how much force causes how much displacement. So, mass attached to spring in our example of simple harmonic motion. What affects the period of a spring? For this one, our equation is very similar but different. It's going to be 2 pi square root the mass of the object divided by the spring constant. So in this case, mass does play a role. It actually doesn't matter how far you compress it or stretch that spring, because of course the more compressed or stretched it is, the greater the force, the greater the acceleration. And so it's going to make up for that extra distance very, very quickly. So the only things that really matter for a mass attached to a spring is the mass itself and the spring constant. And a very similar equation to before. So 2 pi square root mass divided by spring constant. All right, what I want you to work on now, a couple problems. From page 445, let's work on 1 and 3. 449, 1 and 3. We're just kind of focused on the odds here. Page 451, 1, 3, and 5. So those are the problems I want you to work on right now. Work on these. We'll go over these tomorrow. Tomorrow we'll actually do a lab doing mass attached to the spring.